All right, so now on to general relativity, another one of Einstein's theories, which is now going to apply to how we perceive or what we know about gravitation. And so if we go back and think about what we've learned about gravitation, we know that, for an object at the surface of the Earth, we can, given its mass, calculate its weight, and the force would be equal to mg. And that's something that we've seen before, that is also something very similar to, that's an application of Newton's second law, which tells us that if you look at the net force acting on an object F, that's going to be equal to the mass of that object times its acceleration. So Einstein looked at these two effects. So the gravitational attraction, F equals mg, or you can look at universal gravitation, and the definition, so inertia essentially being resistance to acceleration, and thought about, okay, so if we look at this, we could actually see that if you are in a closed system, um, the question is, would you be able to tell the difference? Is it, if you're experiencing a force, is it because you're in a gravitational field, or is it because you're accelerating? Okay, if you think about an object in free fall, and we saw that we can calculate the weight, and the force acting on it is mg, and essentially that means that g is its acceleration, etc., etc. So the idea is, okay, so let's say you enter an elevator and we close the doors, and at that point you don't know where you are. So you're either on Earth, at the surface of the Earth, or you're in outer space, in an elevator that is accelerating at a rate of equal that to g. As it turns out, if you were to drop a ball, or practice any of the projectile motion with the ball that you would on Earth, you wouldn't be able to tell if what you're seeing is because you're at the surface of the Earth, or because you are in a system that is accelerating. So this leads to this principle of equivalence, because clearly, if we can't tell the difference, that means that we have some equivalence between this acceleration and the gravitational field. All right, so the principle of equivalence tells us that all physical experiments conducted in a uniform gravitational field and in an accelerated frame of reference give identical results. First off, you'll see that we're no longer talking about special relativity, because you can see that we are looking at a frame of reference that is accelerating. All right, but what is very interesting is that if you're back to the elevators, really we wouldn't be able to see, if unless we had a window to tell us where we were, we wouldn't be able to see, to know if we were the whatever was going on, happening to the ball, was due to a gravitational field, or to the fact that we were accelerating. All right. And of course, we'll be accelerating uniformly at a given rate. Otherwise, we would definitely see the difference. Now, so this is a very classical example of using a ball and looking at the effects. What if we now looked at what would happen to light? And so if you're in an elevator that is not accelerating and you have a flashlight, you turn on your light, you're going to see a beam straight like this. This is basically what we would be used to. Now, if the elevator started to accelerate, the light would bend. Um, all right. So, according to the principle of equivalence, if you think about it, we are looking at light bending in an accelerated frame of reference. And we just said that the same principle, so the same laws of physics would apply if we were in a gravitational field. So that was very important because that meant that, well, then if you put your light in a gravitational field, it should bend also. Um, and so this is actually something that is pretty hard to show experimentally. But because you need a gravitational field that's strong enough to see the effects of the bending. And this was possible during a solar eclipse. So if you look at the picture, we're looking at what we call gravitational lensing, because you can see that we're now looking at the gravitational field due to the sun, which is much greater than the gravitational field of the Earth. And so you can see that any light that's going to go by is going to bend. And that's why it looks like it's going through a lens, like we've seen in our light chapters. And so what was interesting is that, so during a solar eclipse, there's not as much too much light that you can actually tell what is close to the sun. So by looking from the Earth, obviously, at what was, at essentially stars that were appearing close to the sun, but visible because we didn't have the light from the sun was blocked by the moon. Here, because you could calculate the actual position of a star that would show up. And you can see that. So this is the actual position of the star. So the light here is being bent by the sun. So in terms of our perception from the sun, it's just like what we saw for light. What it looks like, because the ray is coming straight here this way, it looks like the star is actually here. So by looking at the apparent position of the star versus the calculated values that told us that it was actually over here, it was proven that the gravitational lensing was a thing, and that gravitational fields could actually bend light. So this is something that is now used a lot in astronomy, because essentially when you're looking at any given, whatever path of starlight that is hitting the Earth, you have to account for the bending of the light, and also it can give you so it can show you that there is a gravitational field nearby. And so it's very very important, because you can tell the effects due to a massive object that is nearby that you may not be able to see otherwise. So thinking about objects that you cannot see, that have a very large value of their mass, and that will bend light very much. We're gonna next talk about black holes. All right, so black holes um, are essentially very massive objects that are concentrated in a very small space. So if you think about, what we just saw and the bending of the light, and just imagine that you now are looking at a gravitational field that is extremely large. Um, so in what happens with a black hole is that you have a gravitational field that are extremely large, and they're going to bend the light in a way that it will not be able to escape, which is why they appear black, because they absorb the light, and the light cannot escape. So they're very dense, so very massive and very dense. So all that mass is concentrated. And so there is, so we're not going to go in all the details. Again, that's something that we could spend a lot of time on. But you can calculate what's called the Schwarzschild radius of a black hole to kind of give you an idea of how the point where the light can get to and will not be able to escape. um, and by looking at, the escape velocity given the value of the mass of the black hole, the transfer radius is given by this, where you have 2 times g, the universal gravitational constant, m, the mass of the black hole, over c squared, because here we're looking at the speed of the light. And just to give you just a sense of what we would need for Earth to become a so if you plug in the mass of the Earth here, you could calculate the Schwarz radius corresponding to the mass here. So I would encourage you to do this. And so that gives you essentially the sense of where, how what a black hole is going to look like, because technically, the light is not escaping, but you can see the light going in and not escaping. And the cool thing is, last year we had this brilliant picture that was taken for the first time of a black hole. So it looks a little bit blurry, but you may have seen this one. It was going around the internet a lot, because it was the first time ever that we were able to see a picture of a black hole, and you can see essentially the radius there. And the idea is that, so you can if you look at this on this picture here, you can essentially, the center of this thing is the location of the black hole. And the idea is that space itself is being bent by the mass. And so you can see that if you have a small mass, you can have a little ripple. And by having a very large mass, so something like a black hole there, you have something that is very steep, and you can think of light essentially going around that and essentially falling in and not coming out. And so that essentially is a little bit of what you can see on that picture. There is also a lot more that we can talk about, but there's been a lot of research and now measurements of gravitational waves. So essentially, if so, this is a static picture, but as it turns out, there's collisions of black holes, and when that happens, if you look at this kind of bending of space, when you have black holes that are essentially, so the way they collide, they don't collide head on, they do some sort of like this, and then it eventually they collide. But as they're doing that, it's sending ripples, and so those gravitational waves that travel through space, and they have been measured on Earth, which is amazing, because the LIGO experiment, LIGO, was able to measure gravitational waves. And I'm saying it's amazing because even for large events like this, what we can measure on Earth is very minute. So it's a very sensitive experiment, and you're measuring waves, and think about all the background noise that are, all the waves that are contributing on the Earth. So you have all the any kind of earthquake, but anything that is that has a mass is going to contribute something, and it's set up on springs too. So it's a very, very sensitive machine, expanding over large different laboratories, so that they can, if they detect one somewhere, they can detect the same at a very distant location, so they know that it's not an earthquake or something like that. But anyways, they were able to measure those gravitational waves, and further this understanding of general relativity and how we understand gravity. So what is very interesting when you think about, general relativity or gravitational waves, there's still a lot that is not known about gravity, even though it may seem like the simplest force we've ever learned about, because that's what we saw when we studied free fall or projectile motion. As it turns out, there's still a lot we need to learn about gravity and how it works. So again, this is a very short preview of these theories. We just don't have time to go over those in more details. But if you want to learn more, please feel free to ask, and I can send you more information, or we can talk more about those topics. All right, so thank you so much. This is it for our chapter on relativity. Again, if you have more questions, and I know that there may be more questions or answers, because we're just, just getting an intro on those topics. But please reach out if you do have any questions. Thank you. Bye.